In the last lesson video on mass defect, we looked at the origin of delta M in the equation delta E equals c squared delta M, and then we moved on to understanding about the delta E itself, being the binding energy, the energy required to break apart a nucleus into its constituent particles, but also the binding energy is the energy released when the constituent parts come together and bind to form a nucleus. What we're going to look at today is how the binding energy has an impact on the stability of a nucleus, and then come to think about whether fusion and fission will happen for particular nuclei based on this stability. So let's start with stability. And as we are discussing nuclei, I'm going to say that a stable nucleus is more difficult to break up than an unstable one. From there, I can say that a stable nucleus has a high binding energy. The binding energy is the energy required to separate the nucleons to infinity, so large binding energy means we need to put in a lot of energy to break it up. That sounds quite reasonable, but it is actually a bit unfair. Obviously, a large carbon nucleus has lots of nucleons, so it's going to need more energy to break up than helium, which just needs us to separate 4 particles. That doesn't actually mean that carbon is more stable, just as it doesn't mean uranium is even more stable. So I have to improve my view on stability. Let's make it more fair by keeping the same number of nucleons. What if I have 1 carbon nucleus and compare it to 3 helium nuclei? Both have a total of 12 nucleons, but the stability is different. We already know that the binding energy for carbon-12 is 1.43 times 10 to the minus 11 joules. Converting that to electron volts, we divide by 1.6 times 10 to the minus 19, giving 89.4 mega electron volts. Helium-4 has a binding energy of 28.3 mega electron volts, and we have 3 of them, so the total is 84.9 mega electron volts. That's a difference of 4.5 mega electron volts. Joining 3 helium-4 nuclei together to form carbon-12 would release 4.5 mega electron volts. How do I know if energy is released or needs to be put in? I said it's released there, suggesting this fusion reaction releases energy, making it energetically favourable and therefore spontaneous. Let's look into it by looking at the 3 helium nuclei. I'm going to put in the total binding energy, a total of 84.9 mega electron volts, to separate all the constituent particles to infinity. Now, I'm going to combine them together into 1 nucleus, carbon-12, and this time release the binding energy 89.4 mega electron volts. So energy goes in, the particles rearrange, and energy comes out. Since more energy came out than went in, we say this reaction is energetically favourable and may occur spontaneously in nature. It's not going to just happen all the time, since there's an activation energy involved, but doing the reaction results in a net release of 4.5 mega electron volts of energy. Notice that an energetically favourable reaction has the total binding energy increasing. This is not intuitive. An increase in energy is generally not favourable, but this is the binding energy, the energy released, the energy removed when the nucleus formed. A large release of energy means less energy is left behind in the nucleus. This often catches people out. The binding energy is a release of energy, and it's released when the nucleus forms. So, a large binding energy means that a large amount of energy is released, and so a small amount of energy remains in the nucleus. It also means a large binding energy means that we need to have a large amount of energy put in to break the nucleus apart. Finishing off, we have a little more to consider. In physics, we like to be able to compare things neatly, so instead of total binding energy, we're going to refer to binding energy per nucleon. For the carbon-12, the total binding energy was 89.4 megaelectron volts, which gives 89.4 over 12 equals 7.45 megaelectron volts per nucleon. For helium-4, the total binding energy for all three nuclei was 84.9 megaelectron volts, giving 84.9 over 12, since the three nuclei had 12 nucleons still, which equals 7.08 megaelectron volts per nucleon. We can do this calculation for every nucleus and plot a graph of number of nucleons against binding energy per nucleon. The nucleus with the highest binding energy per nucleon is the one that releases the most energy when it is formed, so the most stable. And here is the graph. At the peak is iron 56, the most stable nucleus. Anything heavier than iron 56 can undergo fission to release energy, which is why uranium, which is around about here, can be used. Anything lighter than iron 56 can undergo fusion to release energy, except for this kink here for helium, which is why we can use hydrogen all the way down here in fusion reactors. Actually, this kink is incredibly beneficial. When we do fusion, the energy released per unit mass of fuel depends on the steepness of the curve, the difference between hydrogen and helium. For uranium, the slope is much more shallow, so we need much more fuel to release the same energy. There's also radioactive waste products to worry about, but that's a separate, very important matter. So now we know how the binding energy, or more correctly, the binding energy per nucleon, affects the stability of the nuclei, and we've seen the shape of the binding energy per nucleon curve. We've seen that at the peak, iron 56 is the most stable nucleus, and that has the largest binding energy per nucleon of all the nuclei in this curve, which means that the most energy is released when a nucleus of iron 56 is formed. We've also seen how this relates to fusion and to fission. So large nuclei that are over on this side, over on the heavy side of the curve, will release energy when they become smaller, when they undergo fission towards iron 56, going up the curve. Whereas elements, nuclei to the left, will undergo fusion to release energy and go up the curve. Now, you still need to go over this sort of thing and make sure you're doing some calculations, looking at nuclear reactions and how the binding energy per nucleon is changing. But now you have a good understanding, or at least you have covered all of the core material.